Have you wondered why so many things in our universe spin so quickly due to gravity? Well, that's what we're addressing today on High Peak Education. What's going on, everybody? Another video coming at you here. This time a video involving conservation of angular momentum and how gravity affects the speed of rotating objects in our universe. So let's have a look at the problem. So here we have a problem where there is a spherically symmetric body with some angular momentum L begins to contract under internal gravitational attraction. Assume that the object's angular momentum is conserved during its contraction. Show that the body's rotational kinetic energy must increase. Where does this energy come from? Show that the body's angular velocity of rotation must also increase. All right. So let's assume that we have some sphere here that I have sketched, and it has a radius initially, let's call it Ri. R being radius, I being initial. And suppose some delta t, that is some time later, it has a smaller radius, that is R final. And the sphere has contracted under its own weight, that is under its gravitational attraction. Let's also assume that the mass of the object is constant. So if this object has mass m, that later the mass is still m. So it's the same amount of mass here, the same amount of molecules, and so on. And the idea is that we're going to have certain angular momentum, let's call it L. So L, let's call this L initial. Now, by the way, we don't know what's causing L initial, but let's just assume that this sphere is rotating. So let's assume this sphere is rotating. Maybe it's rotating around this axis. We don't really know. But let's assume that at a later time, it's rotating around the same axis, but I think it should be rotating faster. That's what the problem tells us, and that's what we're asked to prove. So it has a larger rotation, but a larger angular velocity, that is, but I think its angular momentum should stay the same. That is, L initial and L final should be the same. And let's think about why that is. So, if you were to draw some sort of a dashed circle around the system, you could take into account that all the torques are internal. How do I know that? Well, it turns out that when the object undergoes a change in its rotation, all that change in rotation is on the object that we are examining. So I think this is going to be the conservation of angular momentum. So using the conservation of angular momentum, the initial angular momentum should equal the final angular momentum because all the torques are internal. So again, all the tau are internal. Now remember, this is the rotational analog of the generalized version of Newton's second law. Recall that in linear motion, if there's no external forces, if all the forces are internal, then the linear momentum is conserved. There's no change in the linear momentum as a function of time. In the same way, if there's no external torques, if all the torques are internal to the system, then there will be no change in the angular momentum as a function of time. So let's think about what angular momentum really looks like. For a solid body, we know that it should be the moment of inertia times the angular velocity. And I'm just putting the subscript I for initial here for the moment of inertia and the angular velocity. And then that should equal the final moment of inertia times the final angular velocity. Now, in general, moment of inertia is a function of r. And in fact, it's an increasing function of r. So we should say that I increases the moment of inertia as the radius increases. But just the opposite would also be true. As the radius decreases, the moment of inertia should decrease. Now, let's think about what the result of that is. If the radius initial is larger than the radius final, that means that the moment of inertia final should be less than the moment of inertia initial. And as a result, for this equality to be obeyed, the angular velocity final has to be larger than the angular velocity initial. So that's one proof that we have that the angular velocity of rotation must increase. Now, what's another way to say this from the energy perspective? Because here we've only taken the angular momentum and the torque approach. So we were able to get things about the angular velocity. But what about the energy perspective? Well, we know from the energy perspective that rotational kinetic energy looks something like this. It looks like 1/2 I omega squared. That is 1/2 times the moment of inertia, sometimes called the rotational inertia, times the angular velocity squared. Well, what should happen to this? So at some time later, the 1/2, of course, will remain exactly the same. But the rotational inertia goes down. We know that. So that should decrease. So now the rotational inertia is less if you compare the initial to the final. And let's suppose the angular velocity increases. So omega final is larger than omega initial. But when you square that, I think that the final rotational kinetic energy, so this is K rotational final, this should be bigger than the initial rotational kinetic energy. Now, how do I know that? Well, because this conservation of angular momentum equation is exactly inversely proportional. And what I mean by that is whatever factor the rotational inertia changes by, the angular velocity changes by the reciprocal factor. What do I mean by that? Well, as an example, suppose I initial goes down by a factor of 2. So now we only have 1/2 the initial moment of inertia. That's the final moment of inertia. Well, that means the angular velocity should then just be exactly double the initial angular velocity that we had when we are looking at the final angular velocity. But notice, if I multiply this by 1/2, and then I have a factor of 2 squared, that's a factor of 1/2 of the I initial times a factor of 2 of the omega initial, but I square that, I get a factor of, when I work this out, I get 2 times I initial omega initial squared. Notice that the kinetic energy is now double. And let's think about why that is. If you bring the mass inward via gravity, then the moment of inertia decreases, the angular velocity increases. But the angular velocity is quadratic in the kinetic energy equation, whereas the moment of inertia is only linear. So what that means is, as the radius decreases and the angular velocity increases, the kinetic energy starts to go up substantially. Now, what is the result of this? Well, objects in the universe, like for instance certain galaxies that are sort of disk-like, the reason they're rotating so fast is because gravity caused the mass to collapse inward, and so the angular velocity has increased. So hence we have a lot of like accretion disks and objects that spin very fast in our galaxy due to large masses being collapsed in due to their own gravitational force. Another way to think about this is, where did the energy come from? Then it'll answer the last question. Well, you could imagine that the gravity force is doing positive work on the mass. and the gravity force is doing that positive work on the mass because it's forcing it over a displacement, and the force and the displacement are roughly in the same direction, and that means it's doing positive work. And by the work rotational kinetic energy theorem, as the angular velocity increases, the rotational kinetic energy increases. So another way to think about this is that there's a positive internal torque, and we should have an increase in the angular velocity. So there's a slow sort of increase of the angular velocity. So that's an angular acceleration. Thank you for watching High Peak Education. Please smash that like button if you enjoyed this content. Please share this video amongst your social networks, and please subscribe to grow the channel. I look forward to reading your comments, and I will see you in the next video.